Hello, everyone. My name is Debmalya Panigrahi, and I'm going to be talking about covering LP relaxation for the K-server problem and an extension to the case of time windows. This is based on joint work with Anupam Gupta from Carnegie Mellon and Amit Kumar from IIT Delhi. In fact, most of the slides were made by Anupam for a talk he gave on this paper at a different venue. So let's start with the K-server problem. So in this problem, there's a metric space V that contains n points. And there are K servers, K is much smaller than n typically, that the algorithm controls. And these servers reside at various locations of this metric space. The algorithm can move these servers. So for example, in this case, let's say K equals 2, and these two servers are residing at these two locations. The algorithm moves these servers to serve a sequence of requests that arrive online. Each request arrives at some location of the metric space. So for instance, request R1 might arrive at this location, and then the algorithm needs to move one of its two servers to serve this request. Now, the next request R2 might arrive at the previous location that the server was in which case the algorithm needs to either move back the server it just moved, or it needs to move the other server over to this location. In general, on seeing a request R sub t, the algorithm must have a server located at R sub t to serve that request. And if it does not have such a server, then if it does not have a server at that location, then it needs to move one of its servers from a different location to that location. The cost of the algorithm is the total distance moved by the servers on this metric space. And we will denote the optimal cost as the best solution in hindsight. So this is the total movement that the best solution, the one that moves servers the least, incurs given all the requests in hindsight. And as is usual in online algorithms, we will try to achieve the following kind of guarantee. Our algorithms will be randomized, so the expected cost of our algorithm should be at most alpha times the cost of the optimal solution plus some term C prime. So alpha is what we will call the competitive ratio. We aim to achieve the smallest possible competitive ratio that we can. And C prime will be some fixed term that's independent of the request sequence. Now, the K-server problem has been studied for a very long time. It's one of the central problems in online algorithms. So it has a long history. We are not going to be talking about this entire the entire list of results for this problem. But here's a sort of short summary of some of the highlights. So as far as deterministic algorithms go, this problem is fairly well understood. So there's a lower bound of K and an upper bound of 2k minus 1 that's obtained by the famous work function algorithm of Koutsoupias and Papadimitriou. So there is still a gap of 2 between these two factors, but that's not what we are going to be talking about today. Today, we are going to be focused on randomized algorithms. So for randomized algorithms, there's a lower bound of log k, and this lower bound even exists when the metric is very simple, when it's simply a star. This is called the paging problem. Now for paging, i.e. when the metric is a star, this lower bound is tight. So there is an algorithm that also achieves a competitive ratio of log k. But this also extends to weighted stars, as shown by Bansal, Buchbinder, and Naur about 15 years back. But the situation for general metrics is less clear. So in a breakthrough result, Bansal, Buchbinder, Madhuri, and Naur gave a polylogarithmic competitive ratio. But the competitive ratio does have some dependence on the size of the metric space, the number of points in the metric space. And since then, there have been several results that have been proposed for this problem. All of these are polylogarithmic, but have some dependence on terms other than k. So it could be the total number of points in the metric space n, or the aspect ratio of the metric space delta, which is the ratio of the longest edge in the metric space to the shortest edge. But for HSTs, or hierarchically separated trees, we know that there is an algorithm that obtains a competitive ratio of log squared k. And in fact, the results for general metrics are often obtained as a corollary of results for HSTs, because we know that there are there are sort of general standard results that show that general metrics can be embedded into HSTs, losing only logarithmic factors. So in fact, in what I'm going to describe today, we are going to focus only on HSTs. And that would mean that we would lose additional logarithmic factors if we go to general metrics by these embedding results. So what is an HST? I have shown an example of an HST on the right. So this is a tree. So the metric is defined by a tree where the length of edges goes up by a fixed factor. We call that lambda in this example, as we move up from any leaf of the tree to the root. So if the length of the edge from the leaf to its parent is 1, then the length of the edge from the parent to the grandparent of the leaf would be lambda. As we move up, the length of the edges will go up by factors of lambda. So for HSTs, we show the following. First, we give a covering LP relaxation for the K-server problem on HSTs. We believe this is new. It, of course, uses ideas from previous LP relaxations, but as we will see, there are quite a few novel elements to this covering relaxation. Then we give a new algorithm for K-server that uses this LP, and it uses it in slightly non-standard ways. And finally, and this algorithm we finally show has a competitive ratio that's polylog in n and delta. Okay, so one thing to note is that the competitive ratio for HSTs is actually known to be log squared k. So there are better competitive ratios known, but this relaxation has the advantage that it's arguably simpler and more natural, and also sort of gives us more insight into the structure of the problem. Moreover, we show that this relaxation helps us to extend the result to the case where requests have time windows. So this is something that has become quite popular in online algorithms in the last few years. The idea is that now, although requests arrive at a particular time, they don't need to be served immediately. Instead, every request has a deadline, and it needs to be only served by the deadline. It turns out that if all the previous relaxations for K-server, it's very unclear whether they can be extended to time windows, particularly because they don't have this covering structure that our relaxation will have. And previously, for the K-server problem with time windows, the only results known had polynomial factors in K. So this improves the dependence on K by exponentially, but it comes at the cost of some dependence on the aspect ratio of the metric space. For this extension to time windows, our relaxation is quite similar. The algorithm, proof, competitive ratio, all of these are pretty similar to that for K-server. So in this talk, I'm only going to focus on the K-server problem itself, the result for K-server, and I'm not going to explicitly talk about this extension to time windows. Okay, so let's start with this relaxation. So recall that each request in the K-server problem is associated with some unique time. So now let's define our variables as the following. So these would be indicator variables. The variables are indexed by two things. They're indexed by a vertex v in the HST and indexed by some time t. And the interpretation is that this variable xvt is equal to 1 if a server goes from v to its parent p sub v at time t. So if there's a server that's moving from v to its parent at time t, then this variable is set to 1, else it's set to 0. That's the interpretation for variables xvt. We will also use the shorthand x v comma I, where I is an interval of time, to mean the sum of the variables x, v, t, where t belongs to I. Okay, so this is just a shorthand that we are going to use. And now here's the form of our constraints. So let's take any subset of requests A. Okay, so here I have shown a bunch of requests at the leaves, let's say at times 3, 7, 11, 1, and 8. Okay, so this is some subset of requests. The important thing is that these requests are at distinct locations. Okay, so it's a subset of requests at distinct locations. Now let us denote by tau sub v the maximum time of any request from A below V. So for every vertex, we look at the subtree under V, and we look at the request that's the latest from this set A in that subtree. Whatever that time is, that's what tau sub V will denote. So in this particular example, here's how we label all the vertices V by their corresponding tau sub V values. And now, for the purpose of this constraint for the subset A, let's drop all the parts of the subtree that do not contain any requests. So these parts of these parts of the HST are not going to be relevant. So for clarity, I've just removed these from the figure. The constraint says the following. So the constraint says that if I sum up over all the vertices V, the following variables, the variables are x of v, comma, the interval from tau sub v to tau sub pv, where pv is the parent of v. So I look at this interval and I sum this up for all the vertices v of the graph. That sum must be at least the size of A minus k. Okay, so let's look at this in this example. So as you can see that these intervals tau sub v to tau sub pv might be empty for a lot of variables. In this particular example, it's non-empty only for these 4 locations. So it's non-empty for these locations A, B, C, and D. Everywhere else, this interval is empty. So let's just extract the variables corresponding to the non-empty intervals. So here are the 4 variables corresponding to the non-empty intervals, and I've written the variables on the edges because remember what each of these variables represents is a server moving on the edge that the variable is written on in the time interval that the variable has. So the variable on the top left indicates a server moving from A to the root in the interval 3 to 11. Okay, so these are the variables. And the constraint says that these variables should add up to at least the size of A minus k. So in this case, the size of A is 5. So for instance, if k were equal to 2, then my constraint would say that these variables that I have written should add up to at least 3. Okay, and that's the only set of constraints we have. So we write these constraints for all possible subsets of requests. Of course, the number of constraints is huge. It's like exponential. But we write it for all constraints. Structurally, the constraints are very simple. It's just this set of constraints and nothing else. Okay. Now, for those of you who are familiar with the LP relaxation for paging, you would recall you would identify some similarities. In fact, this is an extension of the paging LP, but I won't get into it here. Okay, so the first claim is that this is a valid relaxation of the k-server problem, in particular that if you fix any feasible solution for k-server, then it must satisfy these constraints. Why is that the case? So let's again focus on these constraints on the requests in A. Now, in any feasible solution, these requests are being served by one of the k-servers. So let's partition A into subsets based on which server serves the request in the feasible solution. In particular, let A sub S be the subset of locations that are, or subset of requests in A that are served by a fixed server S. Now, let's imagine a variable x s v of t to be 1 if the server S goes from V to P sub V at time t. Okay, so clearly this is something that the algorithm can pay for, because these variables X are exactly indicative of the algorithm, of the feasible solution moving a server on the corresponding edge. Okay, so now we want to claim that these variables that we have set up X sub Vt, these actually satisfy the constraint that we have. So let's pare down the tree as we were doing earlier, the HST, just to the relevant requests, the locations that have requests from A, and label the vertices by the value of tau sub B, as we did on the previous slide. And then the crucial claim is that if I sum up the value of excess of V from tau V to tau sub PV, over all the vertices V, then that's at least is the size of A sub S minus 1. And of course, if this is true, then I can sum up over all the servers and I'll get the constraint. And I can show that the constraint is valid. So the overall constraint is just the sum of is valid by the fact that the sum of these inequalities, by just summing up these inequalities over all the servers. Okay. So why is this claim true? So imagine that this server S serves a location A at time TA and then location B at time TB, where TB is greater than TA. So here's an example. You take A request at time 7 is at A, request at time 11 is at B. Now let's define C to be the LCA of A and B. Now the claim is that the variables on the path from A to C must actually tile this interval from TA to TB. So the interval from TA to TB is 7 to 11 in this example. And if you look at the variables on the path going up from A to C, their intervals are 7 to 9 and 9 to 11, right? Remember, intervals are tau V to tau of PV. So that means that these intervals actually tile the entire stretch of time between TA and TB. And therefore, if the same server has to serve both location A at time TA and location B at time TB, it must be moving from A to B at some point in the interval TA to TB, which means that one of these two variables on the path from A to C must be set. Okay, so that's a very sort of quick explanation for why this is a valid LP relaxation and why the constraints are valid. So in the very little time that I have left, I will talk very briefly about the actual algorithm. How do we solve this LP? So the algorithm doesn't directly solve the LP, rather gives a sort of algorithm for K-server directly by using the LP as a guide. And this is what the algorithm does. So suppose you have a request at location V0, and this request is unsatisfied at the moment. So then the algorithm will fractionally move servers to V0. And going from the fractional algorithm to an integral movement of servers is some standard randomized rounding technique that I'm not going to talk about. So how does it move servers fractionally to location V0? So we just visualize the tree as a backbone from V0 up to the root, and with subtrees hanging off these backbone vertices V1, V2, etc. And now all that we ensure in our movement of servers is that the set of subtrees at any one level of this backbone, so the subtrees hanging of V1 or the subtrees hanging of V2 or the subtrees hanging of V sub H, each such set of subtrees incur the same rate of cost. So the subtrees under V1 are sending servers at a much higher rate and incurring, let's say, some epsilon cost. Subtrees under V2 are sending servers at a lower rate and incurring the same cost epsilon. Subtrees under VH are sending servers at the lowest rate and are also incurring a cost of epsilon. So all subtrees are incurring cost at rate epsilon. So the total movement cost is just epsilon times the height of the tree in one of these steps. Crucially, we show that the total dual increase for the LP that we just described if we think of these subtree of this movement as sort of as a change in the primal solution, then the corresponding total dual increase is at least epsilon. That's the crucial thing that we end up showing. And we show that the dual is feasible when it's scaled down by an appropriate factor. These two, by standard analysis, gives us the competitive ratio. Now, of course, the two main questions are which server should be moved. So I have only said how much server to move from each of these collections of subtrees, but where do we actually get those servers from? That certainly is guided by the primal LP. And how do we raise duals to ensure that lemma 2 is true? Okay, so this I won't have time to go into, but again, a sort of quick word on this is that we maintain a collection of local LPs. Local LPs are not feasible, but these are sort of LPs on subtrees of the overall tree, which make the additional assumption that the total number of servers in that subtree is constrained to be whatever number of servers the algorithm maintains in the subtree. So this is not a real constraint on the overall optimal solution. So the local LPs are not valid relaxations of the optimal solution, but the advantage of the local LPs is the following. So first, that we can relate the constraints and duals of the local LPs of children to their parents. Okay, and then as we go up the tree, once we get to the root, the local LP becomes the overall LP that we have already shown to be feasible. Okay, and then so basically the charging that we do in terms of the movement cost to the dual happens at the local level, then the local LPs compose and produce the global LP. So the duals in the local LPs actually are accounted for by the dual of the global LP, which in fact is a lower bound or not. Okay, and we show inductively that all the duals are feasible. So that was a little quick, but let me close by saying that we gave this polylog n delta algorithm. And of course, the sort of main questions are, can we get just a polylog k algorithm even for HSTs from this LP? Can we get a polylog k algorithm for time windows? That doesn't exist. And of course, can we get simpler and better algorithms? Thank you for your attention.